So in section 3.1, we took a look at what were called measures of central tendency. In other words, where's the middle or the center of my data? In section 3.2, we're going to take a look at what are called measures of variation. Another way of saying that is measures of, we're going to say, spread. In other words, how spread out or how not spread out is my data. Let's take a look at an example to see what we mean by that. It says this: a testing lab wishes to test 2 experimental brands of outdoor paint to see how long each will last before fading. Makes sense. The testing lab makes 6 gallons of each paint to test. Since different chemical agents are added to each group and only 6 cans are involved, these 2 groups constitute 2 small populations. Okay, so the result in months are shown. Find the mean of each group. Okay, so we're first going to take a look at the mean of each group. Now, we know how to do that. We learned that in section 3.1. So let's do that for brand A. So I know to calculate the mean, I first add up all of my data values. So that's going to be a 10 plus 60 plus 50 plus 30 plus 40 plus 20. Hit enter, I get 210 divided by, I've got 6 total values. So I'm going to take that number and I'm going to divide it by 6. I'm going to hit enter, and I end up getting a mean of, remember our notation, x bar equals 35. Great. Here's what's interesting, and here's where we get to the point of what this idea of variation means and why it matters. If I were to do the same thing here with brand B, adding up all the values, dividing by 6, I would find, let's call this y instead of x, I would find that y bar, guess what, equals 35. It equals 35, just like brand A. Therefore, both brands are identically the same. There's no difference between the two. Or not. They have the same average, but we also want to see, do they have the same, what we're calling, variation? Here, let's start with a simple understanding of what we mean by this idea of variation and why it's significant here. We have this measurement here called the range. The range is the highest value minus the lowest value. The symbol R is used for range, so the formula is R equals highest value minus lowest value. So for this first example here, what does R, and here's a little notation tip of my x value, so R sub x equals what? What is my largest value here? Looks like it's 60 minus, what's my smallest value? 10. Well, 60 minus 10 is 50. So I know that the range, right, so the largest minus the smallest is 50. What about brand B? We'll call this R sub y equals the range of my y variable, which is brand B. My largest value here is 45 minus my smallest value of, it looks like it's going to be that 25 right there, which equals 45 minus 25, 20. Now we begin to see the difference. Even though each brand lasted on average the same amount of time, the range of how long brand A lasted from each sample was much bigger than the range of brand B. Here's why that's significant. Let's ask this question to explain why variation matters. Which brand do you have more confidence in? Do you have more confidence in brand A, which has an average of 35, but could last as long as 60 months, but could only last as long as 10 months? Hey, are you taking a lot of risk there going, man, this paint, I could get a long life out of it, 60 months. But there's just as much likelihood that I'm only going to get 10 months out of it. However, if I go with brand B, I've only got a range of 20, which means my variation away from my average of 35 is a lot smaller. Take a look at that. I know that I could end up, it looks like one of the samples went up to 45, right? So it could last a little longer than the average, but What was the lowest value? It was 25, right? Which means that every sample lasted at least 25 months. So, what do we say? My variation in brand A is much larger than my variation in brand B in terms of this measurement called range. Okay? So, in a lot of ways, this idea of variation, what it communicates is consistency, or it communicates confidence in some ways, in regards to how confident or how likely do I expect my specific scenario to be close to what the expected average is, or do I expect a lot of variation in what we encounter? Let's refine this idea a little bit more, okay? Because we actually have a very specific calculation for this thing called variance, okay? And we'll do an example of this. Okay? Let's take a look at this box right here. It says this: the population variance is the average of the squares of the distance each value is from the mean. There's a mouthful. Let's dissect that here in a moment. The symbol for the population variance is, it's that little Greek letter sigma squared. So sigma squared is population variance. Okay? Now the formulation for population variance is sigma squared equals the sum. Okay, that's what this symbol right here means. It's the sum, so I'm going to add up several things. It's the sum of x minus mu. We remember that mu is what? Mu is our average. So it's saying this: I'm going to take every individual data point and I'm going to subtract my average from it. And then I'm going to square it. And once I do that, I'm going to add them all together. And then what am I going to do? I'm going to divide by n. I'm going to divide by my population size. Okay? Still a little complicated. Let's actually dive in and do an example of how to use that formula. Okay? So, here are the numbers from brand A that we saw in the example we just did. The length in months of how long brand A paint lasted before it began to fade. Okay? Here's how we're going to set this up. We know that we calculated the average mu to equal 35. Okay? What we're going to do is we're going to set up how we calculate this in a table. We're going to first start by listing all of our values x. Okay? 10, 60, 50, 30, 40, and 20. But then what do I need to do? I need to do x minus mu. So x minus mu. What does that equal? What is 10 minus 35, my average? Well, that's negative 25. What is 60 minus 35? That's positive 25. What is 50 minus 35? I believe that's 15. What is 30 minus 35? That's going to be a negative 5. What is 40 minus 35? That's going to be a positive 5. And lastly, what's 20 minus 35? Well, that's going to be a negative 15. Great. So I did this portion right here. I found every x value, every individual value minus the average. So in other words, I found out how far away from my average is each data point. That sounds a lot like variance or variation, doesn't it? Okay, but what does it say I have to do to those next? I have to take each of those values and square them. So my next column here is going to be my x minus mu squared. Great. Excuse me. Okay, well, let's do this. What is negative 25 squared? Now, when you do this in your calculator, be super careful. Parenthesis, negative 25, close parenthesis, then my power button, and then the 2 to square it. When I do that, I get 625. Great. Now I need to do 25 squared. Well, negative 25 squared and 25 squared are actually going to give you the same thing. So I've got another 625 right here. But now I've got 15 squared. So what is 15 squared? It's 225. Good. Oh, this next one we can do in our head. What's negative 5 squared? Negative 5 times negative 5? 25. And then what's 5 squared? There's my 25 again. Lastly, negative 15. I got to square that. Well, we know that when we square a positive and we square a negative, we actually get the same result. So just like up here where we got 225 for 15, I'm going to get 225 for negative 15. Notice what squaring does. It gets rid of all the negatives. So I'm only working with positive values now. Great. But next step is I have to take everything that I just squared and I have to, what does this symbol mean? It's the sum symbol. I have to add all those values together. So I have to take this column right here and add it all up. Let's do that. Let's go 625 plus 625 plus 225 plus 25 plus 25 plus another 225. Hit enter, and I get 1,750. 1,750. Great. So that means I completed everything up here in the numerator. The last step now is to divide by n. N is my population size. What was my population size? It was 6. There's 6 values there. So in order to figure out what sigma squared, my variance is, I need to do 1,750 divided by 6. So let's take that 1,750, divide by 6, enter, and I get that sigma squared is equal to, what was that? 291.7. 291.7. Great. So we calculated this value called variance. Now, variance is useful, okay? But what we're going to find out is that there's another calculation from variance that's going to become hugely important to us, okay? Also, can you see how this process right here can become very cumbersome the more and more data values we get? What if we're working with a data set with 100 values? Doing it this way is going to take forever. It's good to see this process so that we see what's happening, but in a moment we're going to take a look at being able to do this using technology. Okay? But before we do that, we have to take a look at this idea of what is called the standard deviation. Okay? We're going to make a transition. We just got done calculating this thing called variance, but we're going to transition that calculation of variance into something called a standard deviation. And the rest of this course, we are going to be using standard deviation a lot. It's a concept that we're going to apply and need to understand in many different contexts throughout the rest of this course. The population standard deviation, simply put, all it is the square root of the variance. So that value that I calculated, doesn't this piece right here look really familiar? All I have to do now to calculate my standard deviation is square root it. And take a look at this. Wasn't sigma squared the symbol for variance? Well, if you square root a squared, what happens? The square root and the square go away, and you're just left with sigma. So this thing called sigma is our standard deviation, and it is the square root of our variance. If I go up here, my variance was 291.7. So let's find what is the square root of that value, the 291.7. We'll use the full value here. 17 point, I'm going to round to 1. So sigma equals 17.1. This right here is my standard deviation. And standard deviation is exactly what it sounds like. It is the standard amount that each value deviates from the center. In other words, it's an average deviation. It's about how much, on average, how much does each value deviate away from the center? Well, if we go back up here, take a look at this. This value of 10 deviated by 25. This value of 60 also deviated by 25. This value of 50 deviated by 15. This value of 38 deviated by 5. This value of 40 deviated by 5. And this value of 20 deviated by 15. All of those deviations from the center of 35. On average, how much did they deviate? Well, they deviated on average about 17.1. So standard deviation becomes this really important calculation for us to figure out how spread out the data is, right? A small standard deviation would imply that most of your data is really compact and close to your average. A large standard deviation would imply that the data is really spread out and there's a lot of data values that are significantly distanced from the center. Great. So in both of these contexts, we looked at variance and standard deviation in the context of a population. Okay? And in the context of a population, you're going to see this value of n, capital N, and this value of mu. But more often than not, we're not going to be working with populations. We're going to be working with samples, where we have a sample data set from our full population. And what we'll find out is this, that the formulas for variance and standard deviation vary just slightly, but they're still the same exact setup and concept. Let's take a look at this. When we're dealing with a sample, there's two differences. The first difference is, instead of mu, what am I dealing with? I'm dealing with x bar. Well, in 3.1, we learned that we use x bar when we're working with a sample, and we use mu. Both of these are means, right? We use mu when we're dealing with a population. So no surprise there. We'll have x bar instead of mu. The other difference is this. Instead of capital N, we have a lowercase n minus 1. That lowercase n is still the same concept of how many data values do you have, but when we're dealing with a sample, interestingly enough, we don't divide by our entire sample size. We divide by our entire sample size minus 1. So up here, if this was a sample that we were dealing with, instead of dividing by 6, I would have divided by 6 minus 1, which is 5. So that does adjust your variance and standard deviation slightly. Okay? And then also the last thing is the symbol that we use. Instead of, so for standard deviation, instead of using sigma, which is the standard deviation for your full population, we use an S for standard deviation when we're dealing with a sample. And again, this was variance up here. Down here, standard deviation, again, all you did was take this variance and square root it down here in order to get your standard deviation. Okay, so slight variation. It's important to know the concept or the context of your problem. Is the data set you're dealing with a full population, or is the data set you're dealing with a sample from your population? Because these formulas will produce slightly different results. But like I said, when you get large data sets, trying to go through and calculate standard deviation can be extremely difficult. So what I want to do is I want to take a look at using Microsoft Excel to our advantage. Okay? So let's go ahead and take a look at an example from Microsoft, using Microsoft Excel. Great. Okay, so what do we have here? I've got an example over here. The data show the heights in feet of 14 roller coasters. Okay. This is an example we took a look at in 3.1. We found the average height, and we found the median and the mode. And we used that example to find that using Excel. But now we want to find variance. Now notice right here, I have population variance and standard deviation, and I have sample standard deviation and variance. Because remember, the formulas differ just a little bit. They differ in the denominator, where in one you're dividing by the full population value, the other you're dividing by the sample size minus 1. So let's take a look at population variance first. Here's how we calculate population variance in Excel. I'm going to hit my equal sign, and I'm going to type in VAR. And then I'm going to hit the period, so VAR dot, and looks like I have two different options, P and S. P stands for population, S stands for sample. So I'm going to hit P because I'm doing population. I'm then going to open parenthesis. I'm then going to click and hold and drag down and select all of my data points, lift up, now close my parenthesis and hit enter. And there's my population variance, 981.2092. Wonderful. Well, how do I calculate my standard deviation? I could do it two ways. Number one, I could actually just square root that value, and there's my standard deviation. Or I hit my equal sign, and I type in STDEV. That stands for standard deviation. And look, I've got .P and .S. So I'm going to go .P, open parenthesis, highlight all of my data, close parenthesis, and hit enter. And there we go. It square roots the variance and gives me that value of 31.3. So we know that on average, the height of a roller coaster deviates away from the average by about 31 feet. Great. But what if this isn't a full population of roller coasters? What if this is just a sample, which is a lot more likely? How do we calculate variance and standard deviation there? Well, just like we did, so equals VAR, but instead of .P, I'm going to go .S. Open parenthesis, highlight all my data, close parenthesis, enter. You see how that is a little bit different? It's a little bit larger, isn't it? Well, it's because I'm dividing by a value that is one less. And whenever my denominator is smaller, right, my total value will actually be bigger. So we ended up with a slightly bigger value. Standard deviation, same thing, equals STDEV, but I know this is a sample, so I'm going to go .S, open parenthesis, highlight all my data, close parenthesis, and hit enter, and there it is. Then what we expected from the standard deviation, knowing that this is a sample, is a little bit bigger, 32.5. Great. So again, Excel, great tool, because when we have larger data sets, following that formula is really difficult. This allows us to take a data set and calculate variance and standard deviation fairly quickly. Great. Let's go back and take a look at one more example or one context in which we're going to find our standard deviation and variance. Okay. Standard deviation of grouped data. Now, the formula for variance and standard deviation that we're looking at is quite daunting, right? So we've got to take a look at this carefully. We're gonna take a look at how we can use Excel to our advantage for this formula. But what we want to do is we want to take a look at this in a context of an example. What do we mean by grouped data? Let's take a look at an example back over on Excel. Okay, over here, here's the problem that we have. Okay, we've got a problem over here. It says this, that the data represents the number of 20 miles, or the number of miles 20 runners ran in a week. Okay? The data represents the number of miles 20 different runners ran in a week. But here's the thing. I don't have the data values from each runner. What do I have? I actually have a frequency distribution here. I know that there was one runner that ran somewhere between 5.5 and 10.5 miles in a given week. I know that there's two runners here that ran somewhere between 10.5 and 15.5 miles in a given week. I know that I have three runners that ran somewhere between 15.5 and 20.5 miles in a given week, right? So I don't have their actual values. I just have a frequency distribution. Well, here's that formula right here. Can we figure out how to use this in order to calculate the variance S squared of this sample of 20 runners? And then all I have to do is square root it in order to find the standard deviation. Well, yes, we can. So here's what we're going to do. We're going to start right here. I have the sum of f times x squared. Oh, but look at how it says x sub m. That's my midpoint. So what we're going to first do, and then over here we have x times x sub m. And then you sum all of that together, and then you square that value. So how do we accomplish that? Let's take a look first at this f times x sub m. F is my frequency, x sub m is my midpoint. So here's what's really neat. What I can do is I can hit my equal sign, and I want to take this, my frequency, see how it's K5? That's the cell that it's in, K5. And then I'm going to hit my little asterisk symbol. That's the multiplication symbol in Excel. It's Shift 8. And then I want to multiply that by my x sub m, my value of 8. That is in L5. And I'm going to hit Enter. Well, 1 times 5 is 8. Great. I could keep doing that here. 2 times 13 is 26. 3 times 18, figure all of that out. But once I build my formula and I highlight that area, you see the little tiny square, and then it hits it's a solid plus sign. If I click and hold and drag that down, it's going to drag that formula down for all of those rows. 2 times 13 is 26. 3 times 18 is 54. 5 times 23, 115, and so on and so forth. Awesome. Well, let's do the same exact thing for this f times x squared, x sub m squared that we need to do. Well, let's be careful here because now we have a squared value. So this is going to equal my frequency of f, so I'm going to hit that cell, times, now in parentheses, I'm going to do my midpoint here of x sub m, and then I'm going to hit my caret value, which is Shift 6, and 2. That's squaring. That little caret is what gives you the power symbol. So that's going to do L5 squared. Now I'm going to hit Enter. Okay. Did I get the right value? What is 1 times 8 squared? Well, 8 squared is 64. 1 times 64 is 64. Wonderful. So I'm going to do the same thing. I'm going to take this and I'm going to drag it down. Wonderful. Okay. So now what do we need to do? I figured out what my f times x sub m is. I also figured out what f times x sub m squared is. It looks like I need to take both of those and square them. I'm sorry, not square them, but sum them. So here's what I'm going to do. I'm going to hit at the bottom of each column equals the sum, close or open parenthesis, and I'm going to highlight all of those values. Close parenthesis and hit Enter. So it's going to take and add up, M5 through M11, and that equals 490. So I'm going to do the same thing here. This equals the sum of, I'm going to highlight all of those values. Close parenthesis, hit Enter. Great, I found the sums of each of those. Wonderful. Okay, so here's what we're going to do now. Okay, I'm going to take those values, 490 and 13,310. 490 and 13,310. And we're going to transfer those back, and we're going to finish this off by hand. So with those numbers back over here in our formula, can we finish off calculating the variance for that group data? I think we can. So let's get our calculator out, because we have a few more things to do. Take a look at this 490 right here first. That 490, it says it needs to be squared. So let's go ahead and take 490 and square it. Now so 240, 100. Let's do this. So I know that this is going to be a minus 240, 100. Okay? But what does it say I need to do to this 13,310? I need to multiply it by my sample size of n. Now, real quick, what was our sample size? It said we had 20 runners. So I'm going to take that 13,310 and I'm going to multiply by 20. And I get 266, 200. So 266, 200. Now, and all of that's going to be divided by n times n minus 1. Well, what was n? Sample size. So that's going to be a 20 times 20 minus 1. So doing that numerator first, I've got my 266, 200, and I have to subtract from that my 240, 100. And when I do that, I get 26,100. So 26,100 divided by, well, that's going to be a 20 times a 20 minus 1 is 19, right? So that's 26,100 divided by, let's see, what is 20 times 19? 380. So finishing this off, we end up with that 26,100, and we're going to divide that by the 380. And we end up with 68.7. We'll round it off, 68.7. So what does that calculate? That calculates my sample variance for this group data. How do I calculate my standard deviation? All I do is I take that number, so this was s squared. I take that number and I square root it. Square root of 68.7 is equal to, let's find that out. So I'm going to go second square root of that number right there is 8.3. 8.3. Wonderful. So we know that our runners, our 20 runners had an average number of miles that they ran in a given week. And we know that each runner on average deviates about 8.3 miles away from that average. Some on the high side, some on the low side. Some deviate a little less than 8.3 miles, some deviate a little more than 8.3 miles away from the center. But that standard deviation is just on average, how much does each data value deviate away from the center? So in this chapter, deviation, standard deviation is king. It helps us identify a really convenient and helpful, and what we're going to find out, extremely useful way of describing the spread or the variation in our data.